Hi everyone. So today we're going to be continuing to talk about the law of sines, but we'll be doing something a little bit different from last time because last time we were focusing on finding missing side lengths of a triangle, right? We were given information about the angles and we were using the law of sines to solve for the side lengths. In today's video, we're going to be using the law of sines to actually find missing angles from a triangle. And we'll see that we have to use inverse trigonometry to find missing angles using the law of sines. So we'll get there in a little bit. Before we start with that, I just want to kind of share with you some vocabulary that's sometimes used when talking about problems like these. So problems like what we were doing in yesterday's video and what we'll be doing basically all week. So problems where you're kind of like given some information about a triangle and you have to find the rest. So frequently people will refer to the information that is given in terms of using the letter A to represent when there's an angle given and S to represent when there's a side given, and kind of putting them in an order that represents the relationships of what's given. And that probably sounds really confusing, but let me share an example. So if, for example, and we're going to make kind of like I hesitate to call this a table because it's only going to have like two things on it, but it's going to kind of be like a table. So for example, ASA, so that stands for angle, side, angle. And so that would be a situation where you have a mystery triangle and the information that is given about that triangle, the information that you know for sure, let me try to draw this a little better, is one angle, a side length, and then another angle that is on the other side of the side. And let me draw this a little differently just because I want to make sure that we can actually fit our triangle into the shape, into the space that we have. Okay, that should do it. So if you are told an angle measure, a side length, and another angle measure, and they're all kind of next to each other like this, well, that's going to uniquely determine one triangle. So if you are told an angle, a side, and another angle, from that you will be able to figure out using the law of sines what all the other information about the triangle is. But the important thing, or the thing I want to focus on here, is the fact that there's only going to be one possible triangle. So let me write that down and then I'll explain why that is. So number of triangles that fit or fitting the given information. So if you have an angle, a side, and an angle, there's only going to be one possible triangle that goes with that angle, that side, and that angle. And so why is that? Well, if we were to so I used a dotted line, or I use solid lines to represent the information that's given, right? If you're given an angle, you kind of know like what the relationships of these other sides are going to be, because that's what the angles tell you. And you know the length of this side. The thing that you don't know is exactly how long these dotted lines are. But if you think about it, like there's really no other place we could put these dotted lines that would still give us these same angles and same side. Right? If I tried to say, okay, well, why couldn't our triangle look like this? Well, because that has totally different angles than the triangle that's given. Or if you tried to make a triangle that had the same angles, so maybe something like this. So now this has the same angles that were given in the original, but it has a different side length, right? Because this is shorter. So if you know two angles and a side that's between them, there's really only one triangle that fits that description. So on the other hand, let's say that you are given two sides and an angle, and the side that you're given, or sorry, the angle you're given is not between the two sides. So people like to call this SSA. I think you can probably tell why they don't write it the other way. But so let's see what this would look like in a picture. So what do I mean by SSA? I mean that you're given two sides and an angle, but that angle is not between them. So something like this. So you're given an angle, a side, and another side. So this would be angle, side, side. So you don't, in this case, know what this angle is. Maybe let me try to make that more like a dotted line. So this angle would be, it's hard to do. This angle here would be a mystery. The only things that you would know for sure in this case are the angle, this angle here, and these two different side lengths. So in this case, there's actually a few different possibilities for how many triangles fit the given information. So the possibilities are there could be no triangles that fit the given information. There could be one triangle, or there could be two triangles. And so I want to try to show you what that would look like. So the one that we drew here is an example of a triangle where there's really only one possible triangle. And we'll see, I think once we see one that has two possibilities, we'll be able to see why this one only has one possibility. So what would it look like if your triangle, if there was no possible triangle with a given angle, side, and side? Well, if the angle and the side you're given maybe look like that, so that's your angle, that's your side, and then let's say the other side you're given is like only that long. There's no way that you could draw a triangle that has this angle, this side length, and then this other side length. It's not going to connect, right? If you tried to connect this into a triangle, you would get the wrong angle. So that would be an example of what it would look like if you're given an angle, you're given a side length, you're given another side length, and they just don't fit together to make one triangle. So what would it be like if there were two possibilities? So I'm going to try to draw this, and hopefully I will do an okay job. So let's say you know this angle, you know this side length, and then you have another side length, and maybe let me use a different color because so it can kind of contrast. Or actually, yeah, I'm going to use two different colors. So let's say that the other side length looks like this. So in this scenario, and I know this is very abstract right now because I'm not giving you numbers, I'm not giving you anything. We'll do concrete examples in a second, so don't worry about that. But I just want to kind of give you an idea of like big picture what's going on here. So if you're given this angle, this purple side, and this orange side length, but in this situation, you don't know what this angle is. That's not given to you, right? If all the information that you're given is a side length, and one angle that's not between the two sides, you have no idea what that angle is. And so that angle is up for debate. So there's two different possibilities in this case. There's the possible triangle where the angle looks like this, but there's also a possible triangle where you have that same length of triangle, or sorry, of side, but forming a different triangle. So what do I mean by that? Basically, you have two different things that come out of this. And sorry, let me use a different color for this other one so that we can make two different triangles. So there's two different triangles. One would look like this, and the other one would look like this. So all I'm really saying here is that these two triangles that I just drew, they have the same side length. This side is the same in both of them. They have the same angle here, and they have the same of this other side length, this side here. It's just that if all the information that you're given is two sides and an angle, you might not know where that side goes. In this case, we could kind of flip it inward or flip it outward, and either way would give us two different triangles. And so we'll see in a moment an example that's like that. What about the situation where there's only one triangle? Well, looking at this example that I drew first, if we tried to take this side, so this side here, and kind of flip it over somewhere else, it wouldn't fit in the triangle. I'm exaggerating a little bit, but it's a little like too long to kind of fit in the triangle the way that the one did in this example here. So I hope that wasn't too confusing. I think this stuff I know can feel very confusing and it probably feels very vague to you, but we're about to do some concrete examples. Okay, so let's start with an example. Sorry, I'm just looking for it. Okay, so first example I wanted to do is this one. So let's say that we are given A is equal to 30, C is equal to 40, and angle A is equal to 37 degrees. And so the question is to find the remaining sides and angles. Okay, so let's start by drawing some kind of a picture. And so with these, we'll see that like the pictures that you draw can be a little misleading, but it's still good to draw them because basically, at least for me, without drawing it, I feel like I can't really figure out what to do. I kind of need to like visually see everything laid down. But I guess what I'm getting at is that I don't want you to stress out too much about whether your picture is perfect because it's not really going to matter in finding your answer, whether your picture is to scale or not. So I'm just going to draw something. So let's say this is A. So this angle here is 37 degrees. And then we know the side that's across from it is supposed to be a length of 30. And then let's call this angle B. So that one we don't know. And this angle C. And that one we also don't know. But we do know that the length of the side C is 40. And then here we have side B. Okay, so this already is an example of a problem like this, right? It's side angle. So the information that we're given is two sides and an angle, and that angle is not between the two sides. So that's a side angle triangle. And so already you might be able to picture what could give us two different possibilities here. So the way that I drew it, I have this side A here, but we could have a side with the same length that's actually here as well. And so there's going to be two different triangles that could result from this. And we'll see how to get those two different triangles momentarily. Okay, so how do you go about doing this? Well, same as we were doing in yesterday's video, we want to use the law of sines. So remember that the law of sines basically tells you that if you take sine of an angle and compare that to the side length of the side across from it, you're going to get the same ratio regardless of what angle you use. So in this case, just like in yesterday's video, you generally want to start with the information that you know for sure. So what I mean by that is there's one angle and side that we know both of them. And so we're going to start by writing that down. Sine of 37 degrees divided by 30. That's kind of our known ratio. And then, we can kind of go from here however we want. Actually, sorry, I take that back. In this case, we can't. So like we don't know anything about side or angle or side B, right? So we don't want to write down, it would be true to write down is equal to sine of B over B, but that's not going to help us because that's two things we don't know. So what we want to do instead is go to the one that we do know something about. So we don't know what angle C is, but we do know that side length C is 40. So let's try to go through solving this for C and kind of see what happens from there. So if we were to cross multiply like we were doing in yesterday's video, we would get 40 times sine of 37 degrees is equal to 30 times sine of C. So basically what we want to do here is we want to solve for sine of C, because once we have sine of C, we'll be able to use inverse trig to solve for C. So if we divide both sides by 30, and I'm just going to rearrange the way it's written, we have sine of C is equal to 40 times sine of 37 divided by 30. So how can you find C from here? Well, you can take inverse sine, right? If sine of something of an angle is equal to a number, then if you do inverse sine of all this stuff, 40 times sine of 37 degrees over 30, that's going to tell us what angle C is. So if you type that all into your calculator, and again, just like I've mentioned in other sections, you don't want to be typing stuff in right away. You want to really be doing it all in one step. So you should literally be typing this whole thing into your calculator. Or you could type in this part and then say like inverse sine of answer, if your calculator has a button like that. So if you type this into your calculator, you should get that C is approximately equal to 53.4 degrees. Let me just double check that because I copied that down from somewhere and I want to see with my own eyes. So 40 times sine of 37 and oops, I forgot, divide by 30. Okay, so I'm just going to do inverse sine of that. Cool. Yes, I got the same thing that the book did. That's good. So let's keep going with this, and then I want to come back to this moment though. We're going to come back to this moment here and see that there's actually another solution to this. But I want to keep going with this first because this is one of the possibilities, and this will give us one possible triangle. So let's assume that we now know that that this angle C is equal to approximately, what was it? Sorry, 53.4. Okay, so now we can find angle B, right? Because now we know two of the angles, and so we can find the third angle. And so the third angle B, if you subtract from 180, you're going to find that B is equal to approximately 89.6. So that's just by doing 180 minus 37 minus 53.4. So now that we know angle B, now we can find side length B. And this is going to be just like in yesterday's video. So we can use that same, and let me just circle this, we can use that same ratio that we started with here and say sine of 37 over 30 is equal to sine of, and we found that angle B was 89.6, so we'll just put that in there, divided by side length B. And so now we can cross multiply and we get B times sine of 37 degrees is equal to 30 times sine of 89.6 degrees. And so B is going to be equal to 30 times sine of 89.6 degrees divided by sine of 37. And if you type that all into a calculator, you should get that B is approximately equal to 49.8. Okay, so we just figured out that B is approximately 49.8. And I mentioned this, I think, in yesterday's video, but it's always good to do a quick check-in about that the biggest side is really across from the biggest angle, because I think that will help you maybe catch any mistakes that you made with your calculator. So in this case, our biggest angle is 89.6 and the biggest side is 49.8. So that does work out. And then the smallest angle is 37 degrees and the smallest side is 30. So it is true that the small side is across from the smallest angle and vice versa. Okay, so like I said, this is not the only possibility. And so in order to find the other possibility, we have to come back to this moment here. So in this moment here, we jumped from saying that sine of an angle is equal to a number. And from there, we concluded that we could find that angle by doing inverse sine. However, that's actually not really true. So what we wrote down in this step where we did inverse sine, that is one of the possible answers, but it's not the only possible answer. So I want to kind of step away from this problem for a second to discuss that idea, and then we'll come back to the problem. Because I think right now there's a little too much going on in that problem. I think if we just kind of focus on only that issue itself, it will become a little clearer. Okay, so what if we want to, so let's call this the solutions to sine of theta is equal to y. So I'm using theta here instead of A, B, or C, but it's just, I don't know, it doesn't really matter what letter or symbol you use. And then I'm just saying y to stand for any number. So in the example that we were just doing, we had sine of C is equal to all of this stuff. That's a number, right? If you type that into a calculator, it's some number. So I'm just using y to stand for whatever number you're trying to solve sine of an angle is equal to. Okay, so let's think for a second using the unit circle about what it really means to say that sine of theta is equal to y. So that means that theta is an angle, and you know what, I decided just now to change something. I think this will be less confusing for people if I don't use y. Let's pick a random number, and this isn't going to really fit with the problem we were just doing, but it's kind of just a side example. So let's say, for example, we have sine of theta is equal to 0.7. Okay, so if you have an equation that says sine of theta is equal to 0.7, that means that theta is an angle such that the terminal point of theta has a y-coordinate of 0.7. So let's try to sketch what that would look like. So we have the unit circle. So what would it look like to have a y-coordinate of 0.7? So that's going to be somewhere like about 3/4 of the way up, a little bit less. So maybe somewhere like here. So this is one example of an angle. And let me use a different color here actually for contrast. So here is one example of an angle that has a y-coordinate of 0.7, and we don't care what the x-coordinate is. So I'm going to call this angle here theta 1. So I want you to think for a moment, where else on the unit circle is there another angle that also has that same y-coordinate? So I literally want you to pause and like point to your screen and think about where, what quadrant is it in, and like what does it look like to have an angle that has the same y-coordinate. So the angle that has the same y-coordinate would be kind of symmetrically across the y-axis, right? If you go to a point that is also, so I'll say negative x, right, because it's the opposite of the x-coordinate, and the y-coordinate is still going to be 0.7. So this angle would also work. So we'll call that angle theta 2. And so what am I getting at here? Well, both of these angles are solutions to sine of theta is equal to 0.7. So sine of theta 1 is equal to 0.7, and sine of theta 2 is also equal to 0.7. And so that tells us that theta 1 and theta 2 are both solutions to our original equation that said sine of theta, I should say solutions to sine of theta is equal to 0.7. So the issue though is, let's say that we typed inverse sine of 0.7 into our calculator. So which of these angles is it going to give you, right? It's only going to give you one angle, right? The way that inverse trig is set up, it's restricted in order that it like specifically is mandated to only give you one answer. And so if you remember what part of the unit circle inverse sine gives angles from, it only gives angles from negative pi over 2 to pi over 2. And I'm going to write that in degrees actually, because in this section we're really working in degrees. However, inverse sine only gives angles between negative 90 and positive 90 degrees. So if you were to type inverse sine of 0.7 into your calculator, it's not going to give you both of these angles. It's only going to give you the answer, the smaller angle. It's only going to give you theta 1. So the question is, how can we find theta 2? Kind of using that information. And don't worry, at the end of all of this, there will be a rule that you can always use, but I really want you to understand where that rule is coming from. So how can we find theta 2? Well, looking at our picture here, and I didn't do the best job with the symmetry, but this angle here that I'm highlighting in blue is the same as this angle here, right? Because they're symmetric, because these two angles are basically symmetric across the y-axis from each other. And so how can we find the angle theta 2, which is, this part? Well, if we do 180 minus theta 1, because this angle here also has the same measurement, whatever theta 1 is, this blue angle over here has that same measurement. So if we do 180 minus that blue part, we'll be left with the orange part. And so the way that we can find the other angle, theta 2, is we can do 180. So theta 2 is going to equal 180 degrees minus theta 1. So hopefully you can understand why that is, kind of looking at the picture. Okay, so what does all of this tell us? So kind of going back to the original kind of question. So if you want to find solutions to sine of theta, and I'm going to go back to just saying sine of theta is equal to y, just sort of generically any number y. So you can get one answer by doing inverse sine of y. And this is going to give you an answer between, so typically it's between negative 90 and 90, because right now we're working with we're working with triangles. It's specifically going to give you an answer between 0 and 90 degrees, because we're not working with any negative angles right now. And how do you find the second angle? You do 180 degrees minus whatever you got by doing inverse sine. And so this is going to give you an answer that's between, I do that sometimes, too many E's. Answer between 90 and 180. So if you're overwhelmed by all this information and you're looking for what is like that one tidbit you need, it's this. So, and we're about to use this going back to that question we were just working on. So if you're trying to solve sine of an angle is equal to a number, it's not enough to just do inverse sine. That's only going to give you one possible answer. And if you do that, you're going to be missing out on the other answer. So how can you find the other answer? You can do 180 degrees minus whatever you got as your first answer. Okay, so let's see how that works out in this example. So we got as one possible answer here, inverse sine of of all this stuff. So for some reason I'm having issues with my touch screen like all week. So I'm going to go back up here to give us a little more space. Actually, let me make that a little lower. So the other possibility is that C is not equal to inverse sine, and maybe I should bubble this one here too, because it's really both of these facts kind of together. So the other possibility is that C is not equal to all of this thing. It's equal to 180 minus whatever you got from that. So inverse sine of 40 times sine of 37 divided by 30. And so if you type that into your calculator, or if you just do 180 minus what we got over here, right? Because this is the inverse sine of all that stuff. So if you type that into a calculator, you should get, drum roll, 126.6 degrees. So that is the other possibility. And we'll finish off this triangle in a second by finding the remaining angles and sides, but let's just try to draw what that would look like. So basically, this would be a situation where now we would have, again, that same side length, C, and that same angle A that we had in the other picture. But now the difference is that this angle C, instead of being an acute angle, so acute means less than 90 degrees, it's now going to be an obtuse angle. So it's going to be bigger than 90 degrees. And so that means that our triangle has to look more like this. So this is still going to be angle A. That's still 37 degrees. So that's still the same information that was given. This is still side length 40. This is still a side of length 30. It's just that instead of being like this, now we kind of flipped it in like that. And what we just figured out is that that would make this angle here equal instead. So this is C and this is B. Sorry, let me just put that in black. So that would make this angle instead equal to 126.6 degrees. And so if you then do 180 minus 126.6 minus 37, we're left with a very tiny angle for B. So B is just going to be 14.1, or sorry, that's wrong, 16.4 degrees. And so how would we find side length B in this case? Well, now we can use the law of sines again. So we would say, in this case, so sine of 37 over 30, so that was that thing the ratio we started with, is equal to, and then we're trying to find side length B. So we would say sine of 16.4 over B. And maybe for the sake of time, I think we've done a lot of examples like this, so I'm just going to jump to telling you the answer. So you would get that B is approximately equal to 14.1. All right, so that's what I was trying to get at in that first slide where I was just showing you all the different possibilities. So this is an example of a triangle where you're given information that seems like maybe it would just give you one possible triangle, but there's actually two possible triangles. So I want to do a couple more examples. They're going to be a little bit quicker than that one, and we'll see why. But yeah, so let's start with this one. So let's say that we're given that A is equal to 28, B is equal to 15, and angle A is equal to 110 degrees. So again, I'm just going to kind of sketch this. So 110 is bigger than 90, so we know that this triangle is going to have at least one angle that's bigger than 90. So we can make that A. And so it means this is side with length 28. So maybe let's call this angle B. And actually, I'm going to flip that around. Let's make this angle B. And so this is side B, which has a length of 15. And we don't know what C is. So that's the information that's given. So just like the last one, this fits that format of being side-side angle, right? Because we're given a side, we're given another side, and we're given an angle that is not between the two sides. Okay, so let's go through the same process we did in the last one. So we're going to start by writing down the ratio that we do know. So sine of 110 degrees over 28 is equal to. And so then if we look at, what are we kind of prepared to find here? Well, we have to start with angle B, right? Because we don't know anything about C, so that's not going to help us. So we can write down is equal to sine of B over 15. And so we're going to solve this for B. So if we cross multiply, we get 15 times sine of 110 is equal to 28 times sine of B. And so that tells us, just rearranging this a little bit, that sine of B is equal to 15 times sine of 110 divided by 28. So this is where we kind of split off into two possibilities. So the first possibility is that B is equal to inverse sine of all of this stuff. So that's going to give us the acute angle. So again, acute means an angle that is less than 90. So maybe let me just write down here. This is possibility 1. So if you type this all into a calculator, you will find that this will tell you that B is approximately equal to 30 degrees. So if you keep going with this, so let's just write that down. And again, like the last one, I don't think I'll write out every detail of the computation just because it's really similar to examples we've already done. But if we've decided that this angle B is now 30 degrees, so now we can find angle C, right, using just adding up to 180. So C would have to be now 40 degrees. And so now we can say sine of 110 over 28, so that original ratio is equal to sine of 40 over C. So we have sine of 110 over 28 is equal to sine of 40, that's what we found angle C was approximately equal to, over C. And so I'm not going to go through all the steps of that, but if you were to solve that for C, you would find that C is approximately equal to 19. Okay, so let's go back to this place where there's more than one possibility. So basically this stuff. So the second possibility is that angle B is not equal to inverse sine of that stuff, but that it's equal to 180 minus inverse sine of all that stuff. 15 sine of 110 divided by 28. And so looking at what we got for B, we know that B came out to be approximately equal to 30. So if we did 180 minus that, we would get B is approximately equal to 150. So I want you to think for a second or a minute and maybe pause the video and try to think about why is that not a possible answer? So, we know like from this equation, it is a possible solution. Like it's definitely true that if sine of b is equal to this number, it is possible that b is equal to 150. But looking at the triangle that we have, I want you to think about why it's not possible that b could be equal to 150. So the reason it's not possible is because our triangle already has an angle of 110. So if we were to add in 150 to that, that's going to give us something that is too big, right? You can only have 180 degrees in a triangle. So if, we don't even need to bother with finding angle C, because angle C would be like a negative angle. Like it wouldn't be able to exist in a triangle, because in a triangle, the three angles have to add up to 180. And so if our original angle is 110 and then we're adding 150 to that, that's not going to work. And so this is actually, there is no such triangle. And that's because you can't have a triangle with a 110 degree angle and a 150 degree angle. And so basically that tells us that we don't need to worry about this and that there is really only one possibility. So that's why when I wrote out that stuff on the first page, I said that how many triangles could fit the given information if you have SSA? Well, in some cases there will be two triangles. So we saw an example like that first. In some cases there will only be one triangle that works. You just don't really know until you get started. I guess I will say there are ways to know, but I don't want you to worry about that. I want you to just kind of go through the process and see. So I would say when you get to this step, I want you to be aware that there are multiple solutions, and then see what that other solution would be, and then basically see, does this work in my triangle? So in this case, it doesn't, because it would give you more than 180 degrees in your triangle. But in this case, it did. Sorry, let me find here. This case, it did, right? Because in this case, the other angle we got was 126.6. And when we added that to the angle that it already existed in our triangle, it was fine. So it depends on the triangle. Okay, I want to do one more example. So let's say that we're given that side A has a length of 20, side C has a length of 45, and angle A is equal to 125 degrees. So again, that means we have an angle that is pretty big in our triangle. So I'm just going to draw something like that. So this is angle A, 125. This is side length A, which is equal to 20. Let's just say that this maybe is B and this is C. So C over here is supposed to equal to, oops, not 45 degrees, 45 units. And that's it. Let me just add in C is equal to. Okay, so let's go through the process of trying to, again, find the missing information in this problem. I'm just trying to decide on a color. Let's do teal. So same as the other problems, we would write down sine of 125 over 20 is equal to, and so the only thing we can really work on here is C. So we can say sine of C over 45. So if we cross multiply this, we get 45 times sine of 125 is equal to 20 times sine of C. And so if we divide both sides, and I'm just going to reorder this because my brain likes it better like this, we get 45 times sine of 125 all divided by 20. And so we know that we can find our first possibility by taking inverse sine of all of this. Okay. So if you try to type this into your calculator, you're actually going to get some sort of error. So depending on your calculator, I'm not sure what it will say, but it should give you some kind of an error. And so why does it give you an error? Well, if you try to type in just on its own 45 sine of 125 over 20, 45 times sine of 125 over 20, so this whole thing here is equal to approximately 1.84. So I want you to think about for a moment, why would this not work? Like, why would this give you something undefined? And I don't want you just to rely on the fact that your calculator will tell you it's undefined. I want you to understand why this would give you an error. So the reason this would give you an error is because you cannot take inverse sine of a number that's bigger than 1, right? Because what is inverse sine doing? It's trying to find you an angle so that sine of that angle gives you this number. And it's not possible for sine of any angle to be 1.84 because sine is never bigger than 1. So this would have no solution because there is no angle, I'll just say theta, such that sine of theta is equal to 1.84. And so what does this tell us? This tells us that there is no triangle. There is no triangle that has the given description, the given information. So basically, if you are doing one of these problems and you get to a point where you do inverse trig and you're trying to take inverse sine of a number that's bigger than 1, or you just type it all into your calculator and you get an error, that will tell you that there is no triangle, there's no solution. So going back to what we wrote on the first page, now we see the case, we tried to draw a picture here and I just kind of made up what this picture would look like, but apparently it actually looks more like this situation here. Oops. Where the two sides that are given, one of them just isn't long enough to form the correct angle that we know that the triangle is supposed to have. So basically in this video, we saw 3 different cases, right? We saw the case where you get 2 different triangles. We saw the case where you only get 1, and we saw the case where you get 0. I just want to quickly mention that on your homework, I don't think there are any examples where they actually ask you to find 2 different triangles. There's definitely one though where it specifies that the triangle that you're trying to find has an obtuse angle. And so what you want to do on that problem is, so an obtuse angle is an angle that's bigger than 90. And so that's going to be this kind of a triangle. So on that question, just keep your eyes out for that on the homework. There's a question that says, it basically says find the remaining sides and angles. And then it also says something about this triangle has an obtuse angle. And so in that problem, if it didn't specify about there being an obtuse angle, it could be there could be 2 different possibilities. But in order to kind of make there be only one answer, they added that specification. And so for that one, you're not going to be able to just do inverse sine. You're going to have to use this idea, this 180 minus inverse sine idea, to find what that obtuse angle is.